Okay, so the work is done with my PhD student Joseph Ulo, and who is now working in Nairobi. So, okay, so first about the motivation. So, in nature there is infinite number, so in variety of boundary layers adjacent to the free surface, and for example, think about uppermost layer of the ocean as an example. And such boundary layers are usually modeled employing no stress boundary condition at the surface. So the oceanic boundary layer is the key element in controlling the interaction between the ocean and atmosphere, and therefore understanding the physical processes there, and particularly those responsible for mixing, is necessary, and at present it's still quite poor. So the basic fact about this oceanic boundary layer is that it is always turbulent, and sometimes is often stratified because of sun radiation absorbed there, and air entrainment caused by wave breaking. So here we consider new classes of linear and nonlinear instabilities for a generic no stress boundary layer. So this is the model we will be working with. So the blue line is okay, arbitrary shear current of boundary layer type, excuse me, the yellow line, and no restriction on the shape of the this current, and some distribution of density, so of buoyancy. This is Brent-Weisler frequency distributed like that, but it could be any other distribution. What is important that both are localized in the boundary layer. For simplicity, we assume this basic flow to be unidirectional, while the perturbations we are considering are 3D. And what is important, we adopt the Boussinesq closure hypothesis and introduce some eddy viscosity, and assume it to be, for simplicity, constant. Okay, what is the novelty of the model? So that the model deals with essentially 3D perturbations, and which leads to 2D plus 1 nonlinear evolution equations, and dissipation due to turbulent viscosity is explicitly taken into account, and it plays a role, we are considering here very weak stratification, but it does affect considerably development of nonlinear instabilities, which is kind of unexpected, and nobody looked into this problem. And so we consider the situation when nonlinearity, dispersion, dissipations are all comparable. Yeah. So I start with the mathematical model and introduce parameters and scaling. Very brief couple of words on linear instabilities, which and then we go to derivation of nonlinear evolution equation and discuss scenarios of evolution of perturbation. So the starting point are Navier-Stokes equations, and they are pretty standard. So what is kind of specific for this type of law is this boundary, no stress boundary conditions are shown in blue. And so just about the notation, so our vertical axis is is Z, and it's directed downward. And X and Y are horizontal coordinates. Yeah. Okay. So we start with Navier-Stokes equation, which I presented there. And so what are our assumptions? So that perturbations scale we are considering are long compared to the thickness d of the boundary layer. So the amplitude of perturbations, this is streamwise component of velocity of perturbation, are small compared to the value of velocity at the surface. And this smallness is characterized by this same small parameter epsilon. And Richardson number, which is, okay, let's take maximal value n square, and vertical shear is also small and also of order of epsilon. And we also introduce Reynolds number, so using our turbulent, our eddy viscosity. And this Reynolds number is assumed to be of order epsilon minus 2. So to our knowledge, viscous instabilities for no stress boundary layers have never been considered. So this would be analog of Tolman-Schlichting waves in such boundary layers, and to our knowledge, they have not been considered. So, so by employing multiple scale and triple deck, it is straightforward to find the first term of the dispersion relation, which does not depend on the wave number and looks like that. This and it is easy to see that in the convention we adopted U naught dash, that is the gradient of the shear at the surface is negative, always negative. So if triple dash at the surface is negative, there is long wave instability with growth rate of order epsilon squared. So we've got also the next terms in the asymptotic expansion, and they depend on second derivative and fourth derivative of the basic flow at the surface, and verify this numerically, the whole thing numerically. So there is this linear instability, and but in the oceanic context, it's very difficult to measure, almost impossible to measure third derivative, and the fourth derivative is out of the question. So maybe in some other context it will play a role. Okay, the rest of the talk will focus on nonlinear dynamics of linearly decaying modes. So I exclude the situations with instability for the time being, and so we look for the solution in the form of this sum asymptotic series. So this is the same epsilon I introduced there, and crucially to the leading order, we get such a solution for vertical velocity. So the amplitude A is function of depends on two horizontal variables, and slow time is the amplitude of longitudinal velocity. And so what is important, that the dependence on the fast vertical dependence kind of separates. The star stands for convolution. So this is the first term. And so we could expand it so to make it for U naught, it looks in the simplified form, it looks like that. So this is dependence on the fast variable, and this is the dependence on slow vertical scale and slow horizontal and time variable. So so I skip the derivation procedure. So employing multiple scale and a version of triple deck, we get evolution equation for this amplitude. So I stress that for the time being, I'm speaking about non-stratified flow. And so what is important that K is integral operator, and here, in fact, it's so to understand what this operator K is, so let's take Fourier transform of this. So it corresponds to multiplication by modulus of wave vector K. So this is this type of operator. So, and but we use it in X space. We could also represent it in X space, and it looks like that. The integration is with respect to horizontal coordinates. So, but this form is more eliminating in my view. Okay, so this is the evolution equation. This is usual typical nonlinearity, and this is the dispersion which corresponds, as you could see from this form, this is essentially two-dimensional generalization of the Benjamin-Horner equation. This equation was first derived without explicit consideration of viscosity as far as 89. However, the problem with this, the asymptotic expansion is not uniformly convergent. The horizontal velocity components U1 and V1 diverge as z tends to 0. At wave level, it was argued that viscosity would eliminate the singularities, and that has been indeed proved for the free surface flows. So, and what happens near this boundary where there is critical layer? So we carried the corresponding analysis. It's quite substantial, and the main outcome of this analysis, that the critical layer dynamics does not affect the evolution equation. Okay. So, yeah. This equation was intensively studied, and in particular, Dyachenko-Kuznetsov showed that Hamiltonian H of this equation can be written like this, and Hamiltonian can be negative and is not bounded from below. And this implies that for the localized, so for those situations where Hamiltonian is negative, for the localized initial condition, collapse is inevitable. So what is collapse? Collapse is kind of self-focusing, which results in perturbation, developing singularity in finite time. And this is okay. This kind of criterion allows us to take initial perturbations of particular shape and map the domain which find which initial conditions would result in collapse and which will not. So, so this is typical boundary. Say I took initial condition like in the form of Gaussian pulse, and this is the amplitude A, and this is width of the pulse sigma, and all the initial conditions above the curve collapse, and all conditions below decay. So just I don't know. So it doesn't work for some reason. So just a second. Okay, so the movie doesn't work if later on I have extra minute, I will fix this. Okay, now also in certain vicinity of singularity, it was possible to get self-similar solution of this type, so that tau checked tau is time to singular remaining to singularity, and G is function given by this equation, and so and this is how the sample evolution of amplitude. So this is on blue line is amplitude of collapsing pulse with asymmetric Gaussian initial conditions, and here are the parameters, and this red dash line self-similar solution. So at some distance to singularity, the curves coincide. So now let's consider what happens if we take into account the term with Rayleigh friction, which appears due to third derivative at the surface. So when there is no instability, this term gives dissipation, which is characterized by parameter gamma. And for different values of gamma, so we have different pictures of evolution. So this first is with gamma equals 0. This is for gamma 2 then minus 4, and this is 2 times bigger. So what we could see that the presence of this Rayleigh friction it delays collapse, and but the behavior of collapse in the vicinity of singularity remains the same and is captured by self-similar solution. Okay, so this is now we take into account this small stratification characterized by Richardson number of order epsilon, and it gives another extra dispersion term to the evolution equation. And this is the term that gamma we just discussed, which comes from the third derivative of the, yeah. So what we have here, so this new dispersion due to stratification is funny. So look at this term, and so in Fourier scales, in Fourier space, that would mean additional dispersion of this type, and ky is I remind is transverse wave number transverse direction, and kx in streamwise direction. So when there is no transverse dependence, so this term disappears. So this is essentially two-dimensional generalization, which doesn't exist when in one doesn't have 1D analogs. So what we could do similar to non-stratified case, we could get neutral curves for say initial Gaussian pulses. So this is what is done here, and we could see how stratification raises the threshold. So the area above this curve is the area of collapse of collapsing initial conditions, and the area below is stable. Okay, and this is a sample of instead of movie, I showed several pictures how this initial condition evolves with time. And so what is very interesting is that the presence of such very big stratification strongly affects evolution of cross-section of this perturbation. And these are cross-sections at different times. And as you could see, so the evolution is quite non-trivial. At the same time, so for larger times, when we approach collapse, so everything becomes tends to become axially symmetric, and our self-similar solution is axially symmetric, and it applies to this case as well, and agreement is nearly perfect. So I'm coming to conclusions. So we found a novel class, okay, as far as we know, novel class of linear viscous instabilities of no stress boundary layers, controlled exclusively by the sign of U triple dash at the surface. We showed that a wide class of initial conditions evolves into growing coherent patterns, which blow up in finite time, collapse, that's forming component singularity. We found a self-similar solution describing these collapses and showed it to work well in the vicinity of singularity, both for homogeneous and stratified boundary layers, as well as in the presence of friction time. Yeah. For collapse to occur, the initial perturbations have to exceed certain threshold, and the boundary in the parameter space separating the initial conditions leading to collapse is found analytically for arbitrary initial shape. For Reynolds numbers far exceeding epsilon minus 2, and when Reynolds is of order epsilon minus 2, the boundary has to be found numerically for each shape of the initial perturbation. One of the central points that account of weak stratification, stronger dissipation, doesn't prohibit the collapse, it just raises the threshold. And coming back to the oceanic boundary layer, the role of this process in the bigger picture there, in particular in mixing, is an open question on which we are working on now. Thank you.
Thank you, Professor Shrira.